Okay, so but for today, what I'd like to start with is the first part of this list, the study of symmetries, right? And the reason is because when you want to do the quantum theory, you need to have a language that is appropriate for incorporating symmetries, right? And so the formal language is group theory. So they may or may not tell you when you take a quantum mechanics class, but when you get to looking at spin, as we had mentioned already last time, what is spin half? I think I was asked the last time already, what is spin half? What does spin mean? It's really the study of the rotation group applied to the rules of quantum mechanics. So in fact, let's start there as a beginning, as a warm-up, sort of. So rotations. Right. So eventually, I want to get to particularly Lorentz symmetry. The gauge symmetries are important. There are more. If you are a particle theorist, you care about supersymmetry. I will talk about that. I'm not an expert on it myself, but for many decades, people care about that. But as a warm-up, let's talk about rotations, because it's something that is very intuitive, but but it's non-trivial. Once you start to try to put it in a mathematical, more precise language, it's not at all trivial. Right? So let's begin there. So as a start, how do we define rotations? The way we define rotations is to, in fact, make the observation. What is this defining property? That's how we mathematically define rotations. If I have two vectors, and I can use the two vectors to define a dot product. Right? So this is A, this is B. I can simply look at a dot product. A dotted into B, and we know that in flat space, this is just the length of A times the length of B times the cosine of the angle between them. Okay. And that's given two specific vectors A and B. But what rotations tell you, what the defining property of rotations is that as long as I keep them oriented in the same way, I can move them around any way I want. And what rotations do is they preserve the dot product between them. That's what we're going to take as a defining property of rotations. Right? It's a formal, it's the definition. A rotation let's write it as a matrix. So as you know, I can take A, and if I want to rotate it, I will take A and apply the rotation matrix to it. Okay, so this, if we are in 3 dimensions, then this will be a 3-component guy. But actually, you can be in any dimension greater or equal to 2. And it makes sense to talk about rotations. That's in 1 dimension, there's nothing for you to rotate. Right? So this would be D components, and this will be a D by D matrix. And so when you apply to this, what defines our hat to be a rotation is any operation that preserves the dot product of any is important pair vectors. So what does that mean? If I take A dot B, then when I rotate it, what happens is that I will now have, instead of A, I will have R hat acting on A. Instead of B, I would have R hat acting on B. And these two vectors, I will dot them together. But as I said, if you want to preserve the dot product, right, I can do this, I can do that, I can do whatever I want, as long as they remain the same, it gives you the same dot product, then I'm happy. So this has to give you A dot B for any A and B, right? So it's not a specific A nor a specific B. Any A and any B, it has to do this. And if your matrix R hat obeys that property, then we define that to be a rotation. Okay? So we can go further. Okay? So I'm trying to use something that's fairly intuitive to introduce some mathematical rotation. Essentially, at this level is just linear algebra, but I'm just going to use this opportunity to introduce some rotation. So let's write this out in some detail. So the first thing I want to introduce is the Einstein summation, the index notation, and the Einstein summation notation, because we're going to use it very heavily throughout field theory. So if I denote a rotation by R hat acting on A, I can focus on what happens to the ith component. So A to the I is not the ith power of some A object. It's the ith component of my vector A. So let me just write this down. This is the ith component of A. And when I rotate it, the ith component is no longer AI, but rather AR hat acting on AI. But in terms of matrix multiplication, what you are doing is you're taking the ith row and you are dotting it into A. Right? So if I'm going to assume that you know how to multiply your matrices. But how do you multiply matrices? When you take a square matrix and multiply it to a vector, what you're doing is you're taking the ith row of the matrix and dotting it into the vector, and you do it row by row. Right? And so this notation with repeated sum, this repeated indices correspond to summation. Okay. So let me write it down explicitly. So what this means explicitly means exactly what I said in words just now. You're summing over for fixed row I, you're summing over from 1 to D. Remember, this is a D by D matrix against the components of A. Except that because if you have many such operations to do, you will have many summations to write. So supposedly Einstein came up with this notation. I'm not sure this is true, right? But anyway, this is usually what we call Einstein summation convention. Let me write down Einstein summation, which is to say, whenever you have a repeated index, you have an implicit sum over the J, unless you say otherwise, right? So unless you say no sum, there will be a sum whenever you have a repeated index. I should also say, what I will use is that when I do alphabets, English alphabets, these correspond to spatial components. Okay, in this case, we're talking about vectors in space, so that's why I use I. Okay. It's not a universal convention, so you have to check. If you are a relativist, in particular, sometimes you'll find that relativity books use A, B, C as space-time indices. But I will use, in fact, Greek methods to do that. So Greek methods will correspond to space-time components. And I should also add that these guys will run from, 1, 2, all the way to however many dimensions you have for space, right? So usually we have 3, right? Usually these 3. And for Greek indices, it will start to run from 0 to D, capital D. And 0 is the time component. Okay. Yeah, 0. So I'll say it again when we start doing Lorentz symmetry. Now, that's notation, but now we can write this out in some detail. So R hat A, there are different ways of writing it, by the way. So R hat A dotted into R hat B. One way to write this is to realize that this is a matrix multiplication, so you can write it as A dotted into R transpose R acting on B. Okay? But I'll just go straight into the index notation. So what do I have? So when you have an index notation, the dot product itself is just AIBI with a sum over the I. Or I can use something called the Kernel Delta, Kernel IJ, AIBJ. So what is the Kernel Delta? Let me explain that part first, and then I'll come back to this. So what is the Kernel Delta? Kernel Delta is this very simple object. It's basically just an identity matrix. If you view the IJ as the row and the column components, right? So this is 1 when I equals to j. In other words, that's like the diagonal components, the diagonal components. And then is 0 when I is not equal to j. So the off diagonal components. And so this is just a fancy way of saying I'm going to sum over all the I components of A and B, right? Because when you sum over I and sum over J, according to the Einstein Summation convention, you will find that the only time that you get a non-zero answer is when I equals to J. So that corresponds to Kernel II AIBI, but Kernel II is exactly 1. According to this definition. So therefore, this is just equal to that. But notation is important. It gives you a technical crutch to organize your step-by-step analysis. Right? So notation is important because it helps you, it guides you to systematic analysis. Right? So don't laugh at it, as Feynman likes to say. Right? Don't laugh at notation. Proper notation is important. So let's come to the left-hand side, so which is the more complicated part. So we know that the left-hand side is a dot product, but just as we have a dot product between A and B that can be written in terms of the contraction with the Kernel Delta, we can also write this as a contraction between the Kernel Delta. Except now our A and B is now the rotated version. Right? So now we have, on the left-hand side, that's the dot product. Okay? So that's between RA and RB. And we've just discovered this must be equal to connector IJ, AIBJ. Okay? And now we can go a bit further. This is R hat I, M, A, M. So this is just this guy written out explicitly in terms of components. That guy is now R hat J, N, B, N. Connector IJ equals to connector IJ, AI, BJ. Okay. So this takes a little bit of getting used to. Right? If you're not used to seeing lots of indices, I recommend that you should practice. Right? You should work it out for yourself and get used to these indices gymnastics. Right? It is a bit of gymnastics to get used to. Now, let's push on. Okay, so remember now these are all numbers. Okay, so don't get confused. These are all numbers, so I can just put them anywhere I want because it's just multiplication. So what I'm going to do is I'm going to gather the components in the following way. I have R hat IM, R hat JN, and then I have a connector delta here, connector IJ. And then it's contracted with AMBN. Again, I'm not doing anything because these are all just numbers multiplied together, so I can just rearrange them any way I want. And now, remember this is a summation over I and J. So these are dummy indices. I and J are dummy indices. Just like when you do an integration, right? You integrate f of x with respect to x. That's the same as integrating f of y with respect to y, right? As long as it's a dummy index, you can integrate with respect to whatever variable you want. As long as you preserve the functional form of whatever you're trying to integrate, right? Otherwise, the label, what you call x or y or whatever it is, doesn't matter. Same thing for the summation label, right? I can sum over II or sum over kk or whatever. So I can now relabel it as connector MN, AMBN. And the purpose is just so that I can compare things more readily. Why do I say that? Because now, on the left-hand side, what do I have? The coefficient of AMBN is this contraction between two rotation matrices with the connector delta. And on the right-hand side, the coefficient of A and B is just a connector delta. But remember, this has to hold for any pair of A and B. A and B are completely arbitrary, right? Because that's the definition. I take any pair of vectors, remember, and I should be able to rotate them any way I want as long as they preserve the dot product. So it has to hold for any A and B. Therefore, so the fancy math notation is, this is for all A and B. Okay, if you don't like it, don't worry. Just remember that this just means for all possible pairs of vectors. Then, therefore, it must be that the coefficients are equal, because otherwise it wouldn't hold for all A and B. So therefore, we now arrive at actually a new definition of the rotation, what rotation means. Right? So all of that, what I'm just saying, up and down, you can view it as motivation. This is in fact the definition of rotation, of the rotation operator, rotation matrix in D space. It doesn't matter what dimension I'm in, as long as D is greater than or equal to 2. Okay, it doesn't matter. So all I've said is, doesn't matter. I can rotate. I can do this rotation in 2 dimensions, in 3 dimensions, any number of dimensions. The key point is that it preserves the dot product. That's the key ingredient. Any questions at this point? No? Because it's Friday. It's Friday, so nobody wants to talk to me. Okay. So, let me show you that, let me proceed now to show you that if this is the definition of the rotation group, of the rotation, in fact, it obeys exactly what I claimed earlier, that it forms a group. Okay. So of course, to know that, you have to know what is a group in the first place. So if you're taking quantum mechanics, or if you're taking quantum mechanics with me right now, you would know that in quantum mechanics, there's a very important structure called the vector space, right? And the way the vector space is defined is in fact that it has a bunch of rules. The objects in this vector space consist of vectors and complex numbers, or quantum mechanics is complex numbers. And these complex numbers and vectors obey a set of addition and multiplication rules, so to speak, and is closed under these rules. So I'm just summarizing that the formal rules, axioms that they obey, and that those collection of rules is what defines a vector space. So likewise, when we talk about a group, there's also a set of rules that the group obey, right? Actually, it's shorter than the vector space. So let's just I didn't want to erase that because I want to that definition of that. But let's in fact understand what is a group. Yes.
So does it mean that we are just multiply the matrix with a center?
You're asking about this?
Yes.
Yeah, you are. Yeah. So if you are asking, can I phrase it as a matrix multiplication? The answer is definitely yes. So let me write this out over here. Maybe then I can erase that. R-I-N, R-J-N, projector I-J equals to projector N-N. This is the same, it's exactly the same statement as saying R hat, if you view it as a matrix, the transpose of this multiplied by itself gives you the identity matrix. In other words, it's actually just the definition of an orthogonal matrix. Okay. So there are two things to realize here. That the definition of am I answering your question?
Yes.
Okay, good. So the definition of rotations give you two different things that you should realize. This is in fact a group. Rotations are a group. Form a group. And in fact, the group is what you're alluding to is in fact related to orthogonal matrices. What's the group? The group of orthogonal matrices. Okay. And so this is the thing that we need to realize. And orthogonal, and there's a fancy symbol here which goes by OD. Okay. In fact, we will also specialize for now to the case where the determinant is 1. So SOD is the group of orthogonal matrices with determinant 1. Okay, I'll explain this determinant one in a little bit, but let me just do it step by step. Okay? I just want to first introduce. So what the heck is a group, and then we'll talk about the determinant. Okay? Yeah. Yeah, so remember again, all my little a, b, c, all my English alphabet letters are indices. Okay, good. You should always ask, especially at the beginning, if you don't understand the notation, you should always ask. They're indices. So what are indices? They label the component of your object. So R hat itself is a D by D matrix, just to understand. And because there's a D by D matrix, what it means is that R hat I n, for example, is the I row n column of the D by D matrix R hat. Does that make sense? I think I said it was. I didn't write it down on the board. So yes, good. You should always ask, okay? And yes, so this is index form, so the index notation, and this is the matrix notation. Right? And so sometimes there's no one, I think I said this already before, there's usually no one way to write things, right? To express your equations, or even to understand your physical concepts. Right? So this is an example. Be able to go between the two, depending on the situation. Sometimes one is easier than the other. Okay, so let's start with the group. So what is a group? We wouldn't be doing this if symmetries were not important in physics, right? But it is, so we have to talk about it. So a group is a collection of objects, just like if you're taking linear algebra, if you're taking quantum mechanics, just like you know that vector spaces form composed of a group of objects that obey some rules. So it's a bunch of objects which I'm going to just call G1, G2, and so on. These are elements in the group. They can be discrete elements. They can also be continuous elements, meaning there might be some parameter that these group elements depend on. And in fact, we'll encounter such groups. In fact, the rotation group is such an example where it depends continuously on the rotation parameters. But for the basic definition of a group, it just means that there's the first property is closure. Okay, which means that if you take any two elements, G1 times G2, this must belong to the group. So you cannot have such that we cannot have a situation where you multiply two elements and then somehow it's no longer in the group. Right? That wouldn't be a group in the first place. So any product of any two elements must be in the group. The product rule is associativity, so maybe I should put a dot just to indicate product. But this product, you should remember, is not necessarily the same as the just usual multiplication. Right? So for example, matrices are a group, but the rotation matrices are a group. But this dot here would mean a matrix multiplication and not just ordinary multiplication. So you have to be careful here. There's also associativity. So when you multiply three elements together, Doesn't matter how you do it. You do G1, G2, doesn't matter what order you do it. G1, G2 first, and then you do G3, or you do G2, G3, and then you do G1 on the left. Right? So the order is not commutative, but it's associative. Okay? So this is associativity. So when we just say that explicitly, so G1 times G2 is not necessarily, sometimes it is, but not necessarily G2, G1. In fact, matrix multiplication is such an example, right? If you take A times B, and A and B are matrices, that may not be the same as B times A. Right? So likewise, so it may not be commutative. But they are associative. And then there's an identity, which means that there is an element, which in this case called E, and it has to exist. Okay, and so E times any element will give you back the element itself. And then finally, there must be a inverse for every element G. So G inverse times G will give you the identity here that we have defined here. And we can show that the left inverse is the same as the right inverse. Right? So I'm just going to say it. We're physicists, we don't have to be overly. I just want to show you the structure of the group. In math, you have the proof. You have the proof that left inverse is the right inverse. But let me just tell you that it is true. Because we're physicists, we are practitioners of group theory. We're not mathematicians. So these are simple rules, but let's check in fact that this is true for the group that we have just defined, which is SOG. Okay. And so for that, I think I need to erase this part. Any questions for me?
When we consider the orthogonal matrix,
Yeah.
the determinant of the matrix can be 1 or -1.
Yeah,
While
that's
we
right.
always consider
Yeah.
1.
Yeah. Okay, so keep that in mind. Okay, let me try to explain it at the end of this because I want to prove that is a group first. Yeah, but in words, the answer is that for rotations, it should be all determinant 1 for genuine rotations. But the group OD, right, you want to be formal about it, the group OD also contains reflections. And the reflection part is what will give you determinant 1, -1. Yeah. So maybe I'll just say it quickly. So consider the matrix -1, -1, -1. Everybody else is 0. What does this do? This is not a rotation, but it does satisfy this. It does satisfy this. You just take this guy, take the transpose, multiply it by itself. It does give you the identity matrix. But what it actually does is it takes every of your x's and it flips it, right? The x goes to -x, y goes to -y, z goes to -z. So this is a reflection, not rotation. Okay, and so so you see that the determinant of this guy is in fact -1 and not 1. So this is one diagnostic. It's not a foolproof diagnostic, right? So for example, if you have even dimensions, the determinant will be 1 again, right? But again, it's not a rotation. Right? You wouldn't call -1, -1, -1, -1 a rotation. It's a reflection. Right? least restricting it to 1 will ensure that you get rid of some of the reflection. Yeah. Okay. So let's check that R hat transpose R hat equals the identity. All such matrices are formed with okay. So first thing is closure. So what does that mean? So I'm going to take R1 and then I multiply it to R2 and let me call this R3. Okay, so this is definition. I think give me any two rotation matrices and I multiply them first. So for this to be closed under group multiplication, in this case matrix multiplication, what does it mean? It means that this guy had better also obey the same rule. Because this is the definition. Right? Remember, this is the definition of the group. So if this is in the group, this better obey the same rule. Yeah, this is why I put a question mark. Now let's check. So R3 hat times R3, remember, is just R1 times R2 transpose, and then R3 is R hat 1, R hat 2. Okay, so this is the transpose itself, and we can check that in fact by matrix, the rules of matrix multiplication, AB transpose is B transpose times A transpose times R1 times R2. Okay? And this guy here is in fact identity, right? Because I've assumed that R1 and R2 obey. Right? This is an assumption, right? This is an assumption. But with this assumption, and I take the multiplication, the product of the two, I see that firstly this is now 1, so I get R2 transpose R2. But again, this is by assumption identity. Okay. So what it means is that indeed, matrix multiplication, the group is closed under matrix multiplication in the sense that if you take two rotation matrices and you multiply them together, you get another rotation matrix because the answer obeys orthogonality. Okay. And then the rest is, the next one is associativity. Now that's very clear if you remember that matrix multiplication is associative. Okay. And in fact, if you're not used to the index notation, I recommend playing around with it yourself. Using index notation. I'm pretty sure most of you have multiplied matrices before. Right? So you do know that R1 times R2 times R4 does not depend on what order you do it. Right? As long as you do it in sequence, R1 times R2 times R4 is the same whether you do R1 and R2 first, or you do R2 and R4 first. Doesn't matter. But what I mean here is try to write these things out using index notation, right? And then you'll see for yourself that index notation in this case is very useful to to see the associativity property. But anyway, I won't say much more than that. But I assume that is familiar. And then identity. Yes.
You have mentioned that G1, G2 may not be commutative.
Yeah.
So why you approve you can use that means that they
This
are
one?
commutative.
This one?
Yeah.
No, I did not use the fact that, I only used the fact that they are associative. So the product rule is associative. Right. I didn't swap so commutative means I can somehow swap these two guys.
Yeah.
I didn't do that, right? I didn't do that. Are you asking about this transpose operation?
The 1, 2.
Yeah, so don't be confused by that, right? So 1, 2 transpose is 2 transpose 1 transpose. That's not the violation of commutativity. It's the just rule of matrix multiplication. Right? A, B transpose is B transpose and A transpose. Yeah. Good. And so the next one is identity. So I hope it's clear the identity is just, of course, the identity matrix. So if you are working in D dimensions, it's just the D by D identity matrix. Let me just write it down explicitly. Just 1, 1 all the way, and 0 everywhere else. So identity. And then, finally, we need an inverse. But that's exactly the definition. So from the definition, for every R I have, its transpose will give me the identity. So for finite dimensional matrices, that is in fact telling you that R hat transpose is itself the inverse of R. Okay, for finite dimensional matrices, is a theorem. The inverse is unique, and so once you have found the inverse, once you have found a matrix that satisfies this equation, whatever this is, multiplied by R is identity, and whatever this thing is the unique inverse of R. Okay, so we're done because for R hat. For any R hat, by definition of the orthogonal group, you must have an inverse. Otherwise, you wouldn't even satisfy orthogonality in this case. So again, closure, associativity, identity, and there's an inverse for every element. So the reason why I'm going through all this is because there's going to be a very similar analysis for the Lorentz group, which is actually the main point. I'm starting with something that I hope is familiar, because rotation is familiar, you can visualize it. Lorentz group is more abstract because you go to 4 dimensions, and it's hard to imagine 4-dimensional space-time. It's much harder to develop an intuition for special relativity because we don't live in a universe where things move at a relativistic speed. Right? We are not like biological beings. Right? So we have to remember that. We are biological beings living in the universe, trying to understand this universe, but we are constrained by evolution. Right? We did not evolve with a specific purpose of understanding the universe. Right? I think it's an accident. We were constrained, we were evolved to survive as a species on this planet. Right? And so with it comes its own biological constraints. So because things don't move at a relativistic speed, right? You don't have tigers running after you at relativistic speeds. Right? You don't have elephants running after you at relativistic speeds. So you don't have intuition for It's okay. It's normal. Therefore, you should always do this. Whenever you face a new physical concept, use it on something familiar, in this case, rotation. Then we do the rest of it. Okay? So I am probably running out of time. Let's see how much time do I have. Yes. Any questions for me? Because I'm running out of time. Yeah.
I want to ask about the
Determinant.
Yes. A parity matrix is with determinant.
Yeah. In three dimensions, parity is, this is in fact parity, and it has determinant -1.
So parity is Grilling rotation.
Yeah. It's not. Yeah. Yeah. It's not a rotation in the sense that it doesn't have a continuous. So I should say one more thing, right? So rotations have its meaning in the sense that there is a continuous parameter, right? So that we want to associate with it. In fact, that was the next goal. So let me just, in fact, start with 2 dimensions, and then we can make it more concrete. So what I have really defined over there is the group SOG. And of course, there's a lot of overlap between what we mean by rotations and SOG. But there's a little bit more. Rotations in particular are continuously. So I probably should have appended this part of the definition to the mathematical equation over there, right? So what do I mean by that? So for example, in 2D, let's just write it down. In 2D, it's very easy. The most general rotation matrix is just given by cosine theta minus sine theta, and cosine theta. Let me make sure I got that right. The sine, the minus sine is the whole square. Yeah. And so what that does, we'll talk about it more next time, is that it literally takes your 2-dimensional plane and rotates through an angle of theta, right? And so it literally rotates through an angle of theta. So there's this additional aspect of rotations, which is that it depends continuously on these rotation parameters. Whereas parity is just a discrete operation, where you take the x becomes minus x, takes your y becomes a minus y, and so on.
So I can rotate the x.
Oh, you're asking, can I rotate in such a way that I can get a parity, right? Yeah, so in fact, for this case, there's a proof that you cannot. Yeah, so good. Yeah, so let me just repeat the question. Is there, let's do it in 2 dimensions. Is there a r hat of theta such that r hat of theta gives me minus 1, minus 1? Actually, let's do it in let's do it in 2-dimensional space. Okay? It's easier to prove that. So let's not do it here. Let's do it in 3D here. So the question is, in 3D, is there a rotation such that r hat is minus 1, minus 1, minus 1? right? That's your question. Okay? So we can prove it by contradiction. So R in 3 dimensions will depend on a bunch of angles. Okay, so as you know, as you probably know, it depends on two angles, three angles, sorry. It depends on the orientation of your axis, and then how much you want to rotate, right? So there are whatever angles that. But what you want to recognize is that these are continuous parameters, and this is connected to the identity. Why? Because I can just choose my rotation angle to be 0, right? I don't rotate, then that's the identity. Okay? So because it's continuous, so let me draw a boundary here, because this discussion is not the 2-dimensional one. So the determinant of this, so let me just say this is the n hat that determines your axis of rotation. And this is how much the angle of rotation itself. Okay. But because it's continuous, therefore, so because the determinant is continuous, therefore the determinant of this has to be 1. Because, why? Let's take the determinant of both sides, right? So determinant of R hat transpose R hat is equal to determinant of 1 of identity. So it has to be that the determinant of the square of the determinant of R hat must be 1. Right? And so the determinant of R hat itself must be either plus or minus 1. Right? So in case people don't understand, determinant of A, B is determinant of A times determinant of B, but determinant of A transpose is also the determinant of A. So that's how I jump from here to here. There's a few steps here. But the key point is that for all matrices obeying this equation, there are only 2 discrete choices. Either the determinant is 1 or the determinant is minus 1. Okay, so that's the key point. Because it's discrete, and because the rotation matrix itself is continuously dependent on the angles, it can only be 1. Right? There's no way I can tune my angles in a continuous way, right? Because it's continuous, and then suddenly jump from 1 to minus 1 when I take the determinant. It's just not possible, right? The key point is that it's continuous, right? It's a bunch of angles. So, I can adjust angles bit by bit, and because it's continuous, cannot possibly jump from 1 to minus 1. Okay? But now you see the contradiction. The contradiction is that, at least in 3 dimensions, you can prove this contradiction very easily. Just take the determinant. If R hat were equals to minus 1, minus 1, minus 1 on diagonals, then you take the determinant on both sides. Okay. On the left-hand side, we just figured out, because rotations are continuous parameters, continuous matrix functions of the angles. Therefore, this has to be 1. But you can take the determinant of the right-hand side easily, right? So you will be left with the conclusion that 1 is equal to minus 1, right? Which means it's a contradiction. It cannot be. You know what I'm saying? So it's not possible. In 3 dimensions at least, this will be the proof. It's not possible to have a parity, which means you flip all your axes and be able to obtain that through a continuous rotation. Not possible. questions? Yeah, go ahead. You still have questions?
Does the rotation symmetry imply any conservation of
Yeah,
such
yeah.
angular momentum?
Exactly. That's exactly the point. So when that's the other part of why symmetry is important. Right? Symmetry, in particular, let me just say it more explicitly, continuous symmetries always imply a conserved quantity. The continuous part is important. Right. Yeah. So we'll see that. We'll see that more explicitly. But yes, the answer is that it implies the conservation of angular momentum. If you have a total angular momentum, that you have a rotationally symmetric Hamiltonian, right? Because quantum physics is defined by your Hamiltonian. So the precise statement is that if your Hamiltonian commutes with the rotation operator, which in the classical limit just means it's rotationally invariant, then you should expect that your total angular momentum is conserved. Where your spin, your individual spin and the individual orbital angular momentum may not be conserved, but if the total Hamiltonian is invariant under rotations, then the total angular momentum is conserved. Yeah. Do we have more questions? No? Don't be shy. Last question. Yes.
This is the question, what's the meaning of SOP?
It's the more general framework that contains rotations as a symmetry operation. Right. So SOD means let me just write down the name. SOD literally means special orthogonal D by D matrices. Okay. So the orthogonal part I just motivated for you, right? Or you want the matrices to be orthogonal to preserve the dot product. The special part is, in fact, we just elucidated this for 3 dimensions. The special part is the requirement that the determinant is 1, right? And why is that important? Because if you just impose this, again, if you just impose it, the determinant can be either plus or minus 1. But once you impose that it has to be 1, then you rule out things like